Hi there, my name's Avery,
And I'm Ben.
and this is Microbiology, the podcast where it's me, the BMS biomedical science major with accountant.
That knows absolutely nothing about the tiny small stuff.
With tiny small stuff.
The
Yeah.
tiny small stuff.
So today we really kind of wanted to just talk about antibiotics and any resistance that is developing to antibiotics. So Ben, what do you know about antibiotics?
You keep giving me these quiz questions, and I feel like I need to come prepared with a cheat sheet. But I know that antibiotics are for like bacteria, just bacteria, I think. And they can only and they just help fight against like the bad bacteria in your body. I
Yeah,
close.
yeah, that's pretty good. Yeah, that's
Oh, I'll take
that's
it.
correct. Yeah.
Yay.
The only thing I have to add to that, I guess really are two things, is so you mentioned that it only gets rid of the bad bacteria. Now, unfortunately, it does get rid of good bacteria a lot of times, but you're right, it does get rid of bacteria, the bad bacteria, which is the issue too. So the other thing too is you mentioned that it only works on bacteria, which is true because you can't. That's why you can't treat like a cold with antibiotics because a cold is a virus, and you can't treat a virus which is not living, like we said in the previous episode, with an antibiotic, which is to treat something that is living. So first, I really kind of wanted to go into the history of it. So here on the right, we have Paul Ehrlich, who in 1909 kind of discovered the first like antibiotic, and that was this arsphenamine right here, which this is just one possible structure of it. And it was effective in killing syphilis, and he called it chemotherapy. Now, the issue with this drug, which I mean, I don't know if you can see it right here, but these little this little AS, those three, yeah, that's arsenic.
Oh. Oh.
Yeah. So it does succeed. So this drug does succeed in killing syphilis,
But it kills
but
you too.
it also kills you. Yeah. So that was kind of a big issue up front. Was
Yeah.
this? So this dude was on the right track, but he was also, the drug really wasn't effective like long term, I guess is
Yeah.
what I'm trying to say. Now then, around like 20 years later, came this man, Alexander Fleming. So Alexander Fleming, he was studying like bacteria and stuff on like these little plates right here. And he left a plate over the weekend, and he came back to the lab and found that there was this mold growing on it. It's this penicillium mold. And around it, you can kind of see here that these bacterial colonies on this plate, they weren't growing. They were being inhibited by this penicillium. So he found that they were releasing this penicillium mold was releasing this compound called that we would call penicillin now. And penicillin became really our first major antibiotic. And that started really being used in the 40s. So during World War II, when when antibiotics were in pretty high demand.
Yeah.
So that was really our first modern antibiotic. And, compared to chemotherapy,
I know.
penicillin,
Penicillin sounds a lot nicer.
yeah, penicillin really doesn't have any effect, or it won't have any effect on your cells because it's called what we call a beta lactam antibiotic, which we can get into in a little bit more here. They would only affect cells that have a cell wall made of peptidoglycan, which is bacteria. We don't have peptidoglycan, so they can't affect us. So, we just mentioned there are three like major modes of inhibition for antibiotics, and so the first one is cell wall inhibition, which is those beta lactams, like I just mentioned. You also have protein synthesis inhibition, and you also have metabolic inhibition. So first, I really kind of want to go into cell wall inhibition. So you remember, like I said, we don't have a cell wall. And like we meaning humans, we don't have a cell wall for our
Yeah.
cells. And so what these beta lactams or cell wall inhibitors will do is that within the cell wall, there's these little cross bridges between NAG and NAM. Like that's what these little compounds are. They make up the cell wall. And so they make these little cross bridges. Well, these beta lactams, what they do is they inhibit the new crosslinks from being formed. And so these cell walls are going to be, they're not going to have scaffolding. So it's just going to basically just be a bunch of layers of this peptidoglycan that really has no structure to it. So eventually the cell will lose its structure and lyse and fall apart.
Oh gosh.
Yeah. I mean, it's good for us.
Oh yeah, no, yeah, good for us.
Yeah. So this drug basically inhibits a growing cell. And that's kind of one of its downsides, is that it can only affect growing cells, but it's effective in clearing the infection and having it not be worse. So some examples of this would be penicillin, like I just said, the first one, and then vancomycin, which is the more modern version of that. Now we also have protein synthesis inhibition. Now, Ben, do you remember what the ribosome does?
Yeah, it like codes the protein.
Yeah. So it's taking the mRNA and then making a protein from that mRNA. Yeah,
Well, that's what I meant. Mine was the really dumb version of it, but yours is the.
No, I know what you meant. You had it right. You just, I just wanted to clarify.
Yeah, for sure.
Yeah. So with protein synthesis, one of the big targets of that is the ribosome, and there are many different ways that you can target the ribosome. So like in this case, it changes the shape of the ribosome. So this drug, these are called aminoglycosides. They change the shape of the ribosome. So by doing that, it's going to kind of like kink this little mRNA a little bit, like I guess. So you can see how it's like a little bent here. So it's going to change the reading frame for the ribosome. So the ribosome will actually be having the wrong tRNA come in because it's reading the wrong codons because they're bent, if that makes sense. And so this protein will be incorrect. And so like these proteins would be used by the bacteria in some form or another for virulence, virulence is just being able to like spread throughout the body and cause disease. That's pretty much what virulence is. Now here on the bottom, we have what tetracycline does. And so that actually blocks the docking of tRNA altogether, but it just blocks this. There's 3 segments to a ribosome, but the tetracycline is going to be blocking that first section. And so this tRNA can't come in.
Now, can that affect like human ribosomes too?
So bacterial ribosomes and human ribosomes are ever so slightly different. Mm-hmm. So ribosomes actually have 2 components. So like in this component, like this 30S, that describes the size of it. And so like there's this 30S, and then there's this other half, which is bigger, which I believe is 50S, but don't quote me on that. But in humans, we have a slightly different one. We have different subunits. So we aren't inhibited by it because, like these aminoglycosides or like such as streptomycin, they would only affect bacterial ribosomes. Or in this case, the tetracycline would only affect the large subunit, I guess, of the ribosome.
So it's like catered specifically for the bacterial ribosomes, not our own.
Correct. Yeah. And that's why these drugs are pretty good, because they don't have any side effects. Let me rephrase this. They don't affect our own synthesis of proteins, which is sometimes one of the big side effects of drugs. So like I said, tetracycline, that's a big example of a protein synthesis inhibition. And then we also have macrolides, which if you ever take an antibiotic, one of the big things is azithromycin, which, or as Z-Pak is one of the big things. And that's one of those things that just comes in like the little bubble packs, and you're just like, all right, time to take my Z-Pak. Those are like the big antibiotics used now. Like if you ever, I don't know, some sort of infection, bacterial infection, like sinus infection, you can take like a Z-Pak. So lastly, of the topics I really want to talk about for inhibition is metabolism. One of these drugs that really does this well is what are called sulfa drugs. And these sulfa drugs are really important in affecting folic acid synthesis, which is what we can see here. And so these drugs, what they do is they mimic this compound called PABA, which has this ridiculously long name that you and I both don't want to get into. But normally it enters this enzyme right here, and it would lead to folic acid synthesis. But these sulfa drugs, which is this one right here, you can see that they, like this little highlighted shape, they have the same shape here. So this is the sulfa drug. it blocks the enzyme, so the PABA can't enter in, meaning that folic acid isn't produced, which folic acid in bacterial cells is used to make like nucleotides. So like, you know how we were talking last week about like guanosine, adenine, thymidine, like that sort of thing. Like that's what folic acid is used in bacterial cells.
Oh, okay.
Yeah, and so like this, it's really important because then, you know, if you can't do that, then these bacterial cells, I should say, they can't replicate, they can't fix their DNA, and they can't basically anything that involves nucleotides at all, they can't do. And that's as a result of, or I shouldn't say, it's inhibited. And so a lot of times they die because of that, because they can't support themselves. And that's as a result of this sulfa drug. Now, before we really go on, do you have any questions about anything, Ben?
Sure. Which one of like the three methods you just listed is like the like is probably the best at stopping bacteria?
I mean, it really probably depends on what bacteria you want inhibited. I would say probably like protein synthesis would probably be protein synthesis, or like this very specific action right here, this folic acid synthesis. Those would probably be the big ones, because every bacteria is going to use that pathway no matter what.
Okay.
And so they just have to get into the cell, and that's it.
Mm-hmm.
Now, that's also going to bring me up to the secondary topic for today, which is resistance. And so resistance is basically the ability to not be affected by a drug. So even if you're exposing this drug to an antibiotic, which is kind of what we can see here on this plate here on the right, you know, these little discs, they actually have antibiotics on them. And these are bacterial cells, these little, what's what I'm looking for? So here we can see, like at least on this plate here on the left, we can see that there's these zones of inhibition around them, which means that these antibiotics are able to inhibit these cells. And so like there's not going to be any bacterial colonies that grow around these antibiotics. Whereas if we look here to the right, these are resistant strains, like especially these ones right here, like there's no inhibition at all, which means that those cells have become resistant to those drugs. Now, there are four really main ways that this happens that I'm going to get into. And that one of them is you make more of the target to reduce the drug's effectiveness. So I guess we go back here. In order to inhibit or to become resistant to sulfa drugs, you would start producing more of this enzyme. Because by producing more of that enzyme, you're going to require a higher dose of that antibiotic to cause the same effect, if that makes sense. So it's basically just going to become like an arms race of, all right, well, I'll just start producing more. Okay, well, I'll just start, making the dose higher. That's one of the big ones. There's also the mechanism that the cell makes the drug unable to enter the bacterial cell at all. And so like it will get rid of these little like channels that are in the cell. The bacterial cell might just get rid of those channels. And so the drug can no longer pass into the cell because of that. And so obviously it would have no effect on the cell. On the opposite side of that, we also have what are called efflux pumps. And those are involved in resistance because the drug, which is these little pill looking things here, they might get in the cell, but then the cell is going to create a specific pump for those drug compounds or those drug molecules, and it's going to pump them out of the cell. And so they can't have any effect. Lastly, I kind of want to just talk about how sometimes bacterial cells, make enzymes that counteract those drugs. And so that drug can get in the cell and it can stay in the cell, but then the bacterial cell is now creating these enzymes which will somehow change the shape of that drug, which is then going to change its function or deactivate it. Those are really the four big ones. But this last one is probably the most detrimental because it changes the drug itself, as opposed to just making it not able to enter the cell or whatever.
Yeah, it reminds me. I remember in a class we learned about like in like prison sometimes they would give like I think there was an issue with tuberculosis becoming antibiotic resistant because they had the inmates on drug programs, but then they wouldn't finish the drug programs if they left, or sometimes people weren't getting enough doses. And then all of a sudden they saw these antibiotic resistant strains of tuberculosis pop up. And it's kind of like that thought of like, what doesn't kill you makes you stronger kind of deal.
Mhm.
So they said that that was a huge issue.
Yeah, and it's it's kind of behaviors like that that are, that are in fact increasing the resistance. So with like penicillin was not effective really for that long. I mean, obviously, like amazing that it was made, but it really wasn't able to be used that long before resistance developed to it, because that was the only drug we had. So every bacterial infection that we had, we were treating it with penicillin, and so that led to resistance really quick. And even nowadays, there's one really big infection. It's called MRSA, MRSA, which is methicillin-resistant Staph aureus. Staph aureus is a bacterial infection.
Like a staph infection?
Yeah, exactly. Yep.
Okay.
And so if it's methicillin resistant, you can't treat it with methicillin, which is one of the big drugs that are used today. And so it's very difficult to treat it with drugs because we just don't have a whole lot of drugs, because these bacteria are developing resistance so fast. And so that kind of brings me to my next point, which is why it's growing so fast. And that's because a lot of people will ask for antibiotics even if they just have a cold. And as we've discussed quite a few times in this, is that's not going to work for your cold. And if your cold gets better because you took antibiotics, it's not because of the antibiotics. It's because your immune system fought off the infection, or you're just experiencing a placebo effect.
Yeah.
The other issue too, which I never really had thought about before, is our widespread of antibiotics in agriculture. In agriculture, a lot of poultry and cows, they're injected with antibiotics. And so they just have this constant level of antibiotics in their system that even though they don't have an infection, they're still being treated as if they do, so that they don't have sick animals. But the issue with that is that it's causing those existing bacteria in agriculture to develop resistance ridiculously fast, which is why like salmonella, E. coli, and stuff like that, that's why like those develop resistance pretty quickly.
That makes me think like all the time you see like cage free, antibiotic free, as opposed to like obviously there's other animals that grow up in cages and have tons of antibiotics. So it's interesting how like even like today, like they market a lot of stuff that's like organic, antibiotic free, responsibly raised meat.
Mm-hmm.
It's like something that businesses seem to be like positioning to make it appear like they're giving out healthier stuff, which they are.
Mm-hmm. When I first always read antibiotic free, I always read it as more of like, oh, well, there's just not going to be any drugs in my food, which I mean, like that's good in and of itself, but like it's not like it would be that much of an effect on me. The bigger effect is that it's causing resistance really, really, really quick.
Mm-hmm.
Yeah. So on the right here, these are just some of various bacteria that are developing resistance pretty quick. This one on the top left, that's a pretty nasty one. That's for gonorrhea. Yeah, we do have antibiotic resistant gonorrhea.
Okay.
Not good, obviously. MRSA, like we just talked about. Pseudomonas aeruginosa, like that's another one. Also a common skin infection. Strep pyogenes, strep throat.
Mm-hmm. There's my tuberculosis.
Your good old tuberculosis. Yep, that's that, and that's just difficult to treat in general. But that's also becoming pretty resistant really quick. One of the other issues we have as a result of this resistance coming so quick is that we really don't have a whole lot of drugs that we can use that haven't been used on a bacterium before. And so these drugs are they're developing resistance faster than we can develop new drugs. And so eventually we're going to get to a point where we're not going to have a drug to fight an infection.
So it does seem like an arms race almost. Just
Yeah,
new things need to be made, and then the bacteria constantly adapt to it. So that's interesting.
These bacteria, they have such short lifespans. Like we're talking, they can create a new generation in like terms of like minutes to an hour. So they develop changes, they immune mutations, or they can also do this thing called conjugation, which is basically they just are like they connect to each other, and like one could be resistant and one's non-resistant, but then they share their DNA with each other, and it's like, oh, well, now the resistant one has shared its resistance gene with the non-resistant, making the non-resistant now resistant to that drug.
Mm-hmm.
So that's the other thing about bacteria is, they can spread their genes horizontally, which just means within a generation. But it's truly a really bad issue. And a lot of it is just a result of people not properly using antibiotics. In terms of drugs, is the use of like mRNA to treat bacteria now. That was kind of, one of the big things with COVID. So hopefully that proves to be pretty good, I guess, in terms of bacterial use. But possible solutions, short-term use of drug cocktails, which this little picture to the right, I thought that was kind of funny.
Yeah.
But a cocktail of drugs is just like a combination of two or more drugs taken together to increase the effect of those drugs. So the total effect of those three drugs is greater than the sum of those three drugs, I guess, if that makes sense.
Yeah. So like for example, like if you had a drug that like prohibited the bacteria from like spitting out the good drug,
Mm-hmm.
like pairing that together with the good drug would be really good. It would just amplify the effect, right?
Yeah.
Mm.
Yeah. And so one of these we actually use today it's over the counter, but it's a good example of this. It's just a topical cream that you can buy. I forget what it's called, but it has a protein inhibitor in it, a protein inhibitor antibiotic, I should say, a cell wall inhibitor in it, and a metabolic inhibitor in it. So you just rub it on your skin if you have like a paper or not paper, just like a big cut, and it's going to help you pretty well because it's attacking each of those three mechanisms. And the good thing about that is it actually slows the development of resistance because like you're using three different drugs at the same time, as opposed to just relying on one.
Mm-hmm.
So that's kind of like more of like a short-term solution, but long-term, really, we should focus more on relying less on antibiotics because, the more we do rely on them, the less we're prepared to be when that super bug hits that's resistant to all antibiotics that we have.
Mm-hmm.
But yeah, that's really gonna about do it. Do you have any questions, Ben?
No, I think I got the gist of it.
Yeah, I always think like resistance and antibiotics are very interesting to talk about because it's a very social issue, because I just think a lot of people just don't necessarily know that antibiotics can't be used on a cold. So
Oh yeah,
they
you
just
think like,
it's
oh, I'm sick. I need to go to the doctor. Prescribe me something to fix this.
yeah, exactly. And I think that's just something that I think education about antibiotics and the resistance that many drugs are right now. I think that will be pretty helpful for you know possibly slowing down the resistance in these bacterial infections.
Mm-hmm.
Unfortunately, it'll probably be very difficult to stop the use of antibiotics in agriculture, but here's hoping. But yeah, that's really going to about do it for antibiotics and resistance. Tune in next time for our discussion on the immune system.
Ooh, exciting. All right. See you guys.
All right. Bye bye.